bonus episode 69.5, Ice Science, Fire Science, and Energy. Hello, and welcome to this bonus episode of the history of American food. This time I'll be looking at the science around ice and freezing and the energy cycles, and somehow talk about dynamite as well. Oh, and why you can see fire. But I feel good about this because explosives and ice and freezing are all going to be incredibly important in food transport as the railroads happen and change the whole American food landscape in the second half of the 19th century. And seeing fire matters when it comes to cooking, along with reading and testing theories of relativity and stuff. But as usual, I'm getting ahead of everything. So pull up to your place at the lab table, put on your safety goggles, and no eating in the lab or you might turn into a dinosaur. Let's talk about how stuff gets frozen, blows up, and lights on fire. That's right, it's former chemistry teacher time. And these topics are some of my favorite pieces of information from those days. Some of the information even has a certain amount to do with why I ended up becoming a chemistry teacher in the first place. The big question, why, if you take a bag of plain old water ice and add plain old salt, or better yet, rock salt, how does it make a liquid that's actually colder than the ice it used to be? How is a liquid colder than the solid? Aren't solids the frozen versions of a material? So obviously the solid should be colder, right? And this was the problem 8-year-old me was having, trying to figure all of this out while cranking homemade ice cream. And my dad, sorry dad, telling me that's just how it works. The melting makes it colder. Dad's more of a computer guy, and from the days when you had to work to make computers compute, punch cards, vacuum tubes, storage happening on magnetic tape and huge disks you could mess up with a stray magnet. So I forgive Dad for not being good at explaining the energy values and the results of bonds breaking and bonds forming in water and the salt mixture. And I did end up as a chemistry teacher and then took a left turn into food curiosity, so the results weren't all bad. Since I don't know where you're coming from, and this information is pretty cool, and 100% unknown in the 18th century, I'm going to start at kind of the chemistry understanding of how atoms work. The closest thing the alchemists and the newly minted chemists had to atomic theory in the 18th century was ideas derived from alchemical exploration, that there were pure substances, stuff that couldn't be broken down anymore, stuff that was just like one thing. Things like gold and sulfur and iron and mercury. Other things they were unclear about. Was water a pure substance, or was it made of a combination of stuff? Part of the problem here is that gases were not understood well or even particularly recognized as stuff. Heat and cold were thought of as different things and were considered to be fluids. Maybe, I don't know. Count Rumford, who I'll talk more about in the 19th century, was one of the first guys to really start to ask some of the important questions about gases and heat, along with other chemistry guys you've probably heard of, like Lavoisier and Boyle. Once gases are recognized as real and chemistry starts to understand gas pressure, which required the development of airtight stuff and vacuum pumps, atomic theory as we know it started to have a chance. Rumford was one of the first to posit that heat was a ray rather than a fluid, which was an important step, but he also posited cold rays, so baby steps. So no useful atomic theory in the 18th century, but here we are in the 21st century, and we are way past atomic theory, that there are atoms, and we have subatomic theory, that those atoms are made up of stuff. Electrons and protons and neutrons. And then we have subatomic or quark theory. That is, the things that make up the atoms are themselves made up of quarks and other things. But don't worry, we get to stop at the intersection of atoms and their parts. That is all we need to know to get through why salt water is colder than ice. So water. Pure water is a molecule, which means it's a chemical made up of two or more atoms. Yes, like everything else that is stuff in the universe, water is a chemical. And in this case, water is made of one medium-sized oxygen and two tiny little hydrogens. There are also big, jumbo, and ridiculously unwieldy atoms out there, but most of the world, well, Most of the galaxy and even the universe are made up of a handful of practical small and medium-sized atoms, and the rest of the stuff acts like interesting sprinkles. Getting into all that likely belongs in a 20th century episode when concentrations of these sprinkle elements start showing up in food in bad ways. But back to water. The way these three atoms arrange themselves look like the most regular cute sketch of a mouse head. My elementary school visions of water molecules were simply seeing Mickey Mouse's head all over the place. Oxygen is number 8 on the table of the elements. That means it has 8 protons. Protons give every element its identity. Atoms are just a number to the universe. And oxygens usually have 8 neutrons as well. They can occasionally have a different number of neutrons, which would make them an uncommon isotope. But that's unusual and is a more common phenomenon in the big clunky elements down at the bottom of the table. I'll explain more about isotopes when I do my food irradiation episode, and that is way in the future. If you're wondering, it will involve astronauts and sending food to space. For our purposes, we are working with nice normal oxygen that makes nice normal water and has a nucleus made of the unchangeable 8 protons and the boring most common 8 neutrons. These two particles contain, functionally, all the mass of the oxygen, hang out together in the nucleus, giving the oxygen, like every single other element, an incredibly dense core. Then, on the outside of the oxygen atom, buzzing around so fast that they make a cloud, are 8 electrons. Electrons have an opposite charge from the protons. Thanks to Benjamin Franklin and his messing about with kites and keys and lightning and rabbit fur and amber, these charges were arbitrarily determined to be negative for electrons and later positive for protons. Okay, Ben Franklin didn't know about electrons, but they called it a negative charge. Anyway, there's a great fight in there where some people claim chemistry and physics math around electricity would make way more sense if electrons had been given the label positive. But that's a convention unlikely to ever change. So here we are. Oxygen has 8 neutrons, which are neutral. They have no charge, 8 positive protons, and 8 negative electrons, making oxygen, like every solo atom in its idealized state, neutral. But here's where we get unideal. At the end of the 19th century, the idea of the electron cloud had been figured out. In the 20th century, it was determined that this cloud was actually organized and it had layers. So that dense core of protons and neutrons compared to the entire area of space an atom takes up is pretty small. The electrons, which are teeny weeny compared to their partners in the nucleus, are buzzing around very far away. You can kind of think about it as if the nucleus is a star and the atoms are the planets or asteroids or something rotating about the nucleus. But, unlike planets, the electrons are not nice and localized. You can't really say the electron is there the way you can say a planet is. Electrons exist as more of an orbital, which for our purposes is basically a shaped cloud. And the relative distances are much larger in the atom. If the nucleus of a hydrogen atom were the size of the sun, the electron would be about 6 times as far away as Pluto. Earth is 8 light minutes away. Pluto is about 5.5 light hours away. So the closest electron would be 33 light hours away. That's like almost a light day and a half. Okay, enough with the extremely big and the extremely small. What really matters is thinking about an atom as a solar system is fine if you just don't get too literal. Now, it's only that outer layer of electrons that do anything in chemical bonds or chemical reactions. All the other electrons are just foundation. I mean, they have to be there or things don't work, but they mostly don't get to do anything. Okay, unless there's things like lasers or plasma or stars involved, but no lasers or plasma or stars here. In every atom, the first layer or orbital that electrons go into has 2 slots. And these 2 slots like to be either all empty or all full. That's it. Which will explain why hydrogen acts the way it does when we get there. But with oxygen, which has 8 electrons, those 2 slots are filled. The next layer of electrons has 8 slots. And if you're following along with a periodic table of the elements, which I will have a picture of in my show notes and links, you'll see a pattern developing here. Further down the table, things get more complex, but we don't have to go any deeper. Anyway, stow 2 electrons in the foundation layer, and then you have 6 electrons left to go in the next layer that likes to have 8. The 8 electron layer, just like the 2 electron layer, also likes to be all the way full or all the way empty. That's why the noble gases, stuff like helium and neon, don't really react with anything. They prefer to just sit there taking up space because their electron slots are perfectly full. The all-empty preference gives us positive ions, and the full preference gives us negative ions. And this is why oxygen and hydrogen, when all alone, are so reactive. So, oxygen only has 6 electrons to put in those 8 slots. The atom wants to have those slots full so badly, it is willing to go borrow or even steal electrons from other elements, or just pick up loose ones that are lying around, and at the atomic level, both these things are possible. When it picks up loose electrons, oxygen gets a -2 charge and is all set to make connections with other ions or molecules that have positive charges. It's in a pretty unstable, highly reactive state. Now, when it borrows electrons from other atoms, it forms a bond. But before we get into bonding, let's move over and look at hydrogen. Hydrogen is 1 on the periodic table. It has 1 proton. It also usually dispenses with its neutron. Hydrogen's weird. It just is. Don't worry about it too much. But that means it only has 1 electron, which we know means that the first layer of the electron cloud, which prefers 2, only has 1, and this is no good. So along with the neutron, hydrogen prefers to also dispense with its only electron, and will do this by just getting rid of it, which makes a hydrogen atom all on its own typically positive, so ready to connect with anything negative that comes along. Now, if you remember a few things from chemistry, it's that hydrogen and oxygen, when left to their own devices, don't hang out as single elements. They prefer to be in hydrogen molecules, H2, or hydrogen gas, and oxygen molecules, or O2, oxygen gas. This lets them borrow electrons from the other hydrogen or the other oxygen atom, and that way they create a full part of the time electron layer. 2 electrons around the hydrogens, each borrowing the one from the other about half the time-ish, making that 2-slot orbital full. This is not a super stable arrangement, which makes H2, hydrogen gas, pretty unstable and willing to burst into flame and perform all sorts of chemical reactions pretty easily. You can't yell at a cloud of pure hydrogen and make it explode, but a pretty low energy spark will do it, including regular old static electricity. O2, it's a bit more stable, but hanging out in an atmosphere of more than the normal 20% oxygen we live in is a dangerous proposition. Flammable materials in an oxygen-rich environment, given a spark, will start combining willy-nilly to form new chemical compounds. The kaboom part of the book and movie The Martian are an excellent demonstration of this. One of these new preferred, very stable compounds is water, another lesson from The Martian. This is because the oxygen wants to hang out with 2 extra electrons, and the 2 hydrogens want to mostly never see their electrons. So the oxygen gets its full 8-slot orbitals, and the hydrogens have nice empty ones. And the resulting H2O, it's nice and stable. Okay, you ask, quite reasonably, what makes a stable bond or compound or chemical versus a volatile one? In electron terms, it mainly means that electrons are in full or empty orbitals the way they like to be. The more the electrons are in a formation they like, the more energy it takes to kick them out of where they want to be. If the bonds are a bad compromise, that is, the electrons kinda get where they want to be, but it's a bad sharing arrangement overall, they aren't well set in their preferred orbitals, it will take a lot less energy to kick them out of the bond orbitals they're in and ready to bond with something else. That's an unstable bond. Now, if you remember anything about physics, even at the Snapple facts level, you know the energy of the universe is absolute. It can't be created or destroyed, it just moves around. When you get stars and other energy equivalents involved, you can sometimes make energy into matter and matter back into energy, but it doesn't go away. Well, when you form bonds, energy is released into the local area. A weak bond, a small amount of energy is released. A strong bond, lots of energy is released. And we, as humans, with a certain set of sensory abilities, sense that energy release as heat. Occasionally as light, but mostly as heat. Which brings us to dynamite. The original dynamite was based on nitrogen compounds, the most famous of which is nitroglycerin. Nitrogen, the atomic number of nitrogen is 7, which means it has 7 protons and 7 electrons and most often 7 neutrons. The way nitrogen gets happy is to make 3 bonds. You can see on the periodic table that it's 3 away from the end. Dude, periodic table holds so many secrets. I'll link a fun podcast episode and a pointer to a cool book on this if you're curious about more of the periodic table stuff. Anyway, nitrogen is a pretty common element and hangs out in our atmosphere as N2. 80% of the air is N2 gas. It's everywhere, but it's also inert, which means it doesn't react with anything else unless you dump a whole bunch of energy into it. This is because nitrogen gas is one nitrogen atom very, very stably triple bonded to another nitrogen atom, and a very large lot amount of energy gets released when that bond is formed. This means 2 things. And this will be super important information when we get into the 19th and early 20th century and artificial fertilizer becomes a thing. But right now, it matters for why nitroglycerin and other nitrogen-based explosives go boom the way they do. Nitroglycerin on its own is incredibly unstable. The invention of dynamite was figuring out how to suspend nitroglycerin so it wouldn't just explode every time somebody just looked at it wrong. Dynamite holds nitroglycerin in a suspension where you can say drop a dynamite or maybe even step on one, but you can't leave it next to a fire where dynamite might get too hot, and you can't smoke around dynamite where you might drop some smoldering hot ash on them and then cause something to burn and then go boom. But a blasting cap, something little and even easier to set off than nitroglycerin and such, and later electric sparks were enough to destabilize the nitrogen-based explosives and bust apart the unstable, low-energy bonds. Then these nitrogens, along with the carbons, hydrogens, and oxygens, free of the bonds they did not like, look about for something better, something more stable. For nitrogen, that was another nitrogen atom, and that formed that triple bond, which releases a whole bunch of energy super duper quickly. Water and carbon monoxide and oxygen are also all formed when you have this explosion, and all that energy released as heat expands all the gas all around it, including the newly formed N2 and H2O and CO and O2. And all that hot, rapidly expanding gas violently shoves stuff out of the way. Kaboom, as they say. Over time, we have developed explosives that are more stable. So when they are at last activated, they create final products that release even more energy, but it's still all bonds breaking and forming and throwing energy out into the universe. This sort of thing is happening on a smaller scale and more slowly when things burn in a fire. In the cooking fires of the 18th century and all the way back into the misty past, wood is the main thing that was burned. Wood is basically a whole bunch of carbon, oxygen, hydrogen compounds with some nitrogen and other stuff that are looking to reform into water and carbon dioxide and a few other things. Many of them much more stable chemicals than wood. We know this not just because wood burns and produces these things, but because left to its own devices at room temperature and colder, if wet, it will rot and get broken down by all sorts of bugs, mushrooms, molds, and bacteria into these same things, just much more slowly. When wood decomposition happens fast, that is, it burns, some of the energy release happens in such a way that it is so energetic, some of the released energy moves out of heat wave territory into visible light territory. Heat energy and visible light energies are on a continuum, all the way up to UV rays, gamma rays, X-rays, that stuff. Infrared or heat radiation and radioactive radiation are all on a continuous scale. We just experience them in different ways. So the energy releases that happens in fire, lots, are in the infrared range. It feels warm, but some of it's in the visible light spectrum. We can see them, and they emit light waves that bounce off stuff that makes the other things visible to us. I'll probably get into the temperatures and colors of visible fire when America starts using fossil fuels to cook its food. Okay, so I've covered why dynamite goes boom, why we can see fire, but how does that get us all the way back around to how salt and ice make a liquid cold enough to freeze ice cream and make other ice? So let's get to the end and wrap this up. So we have to get back to bonds. Now, one fun or confusing thing in the molecular world is that there are several kinds of bonds. The bonds I've been talking about so far are called covalent bonds. These are the strongest ones because the electrons are shared between atoms. They cause the most spectacular results when you break and form them. But there are two others I will cover here, and they each help to explain the water colder than ice phenomenon. Another kind of bond is the ionic bond. This is what you find in salts. Sodium chloride salt, of course, but all the other salts as well. For more on this, you can go back to my extra salt bonus episode number 10.5. All we really need to know now is that while covalent bonds, the ones that hold together water, all happen between nonmetals. Ionic bonds happen between a metal and a nonmetal. Sodium chloride, our table or rock salt, is the metal sodium, and the gas, a nonmetal, chlorine. And if you look at the periodic table, they are each one away from a noble gas. Sodium has one electron in an otherwise empty outer orbital, so it's looking to offload it. Chlorine is one away from full. Again, happily swiping any stray electrons out there to fill it up. So sodium becomes +1 because it gave away a negative. Chlorine becomes -1 because it picked up an extra negative. And these two charged atoms, that is, ions, happily snap together like sort of atomic Legos. A strong bond, but they can also be popped apart by tempting positives and negatives out there, which is what happens when you put salt in water. The positive ends of the water, the hydrogen ears on our mouse, attract a chlorine, and the sodium is attracted to the negative oxygen head of our mouse cartoon. That's all it takes. A little heat energy is lost from the water because popping apart the NAs from the CLs takes energy, but not a ton, just some. And the very weak attraction to the water molecules releases much less energy. One example of salt dissolving that sucks up enormous amounts of energy, by the by, are those really neat instant cold packs. They're filled with ammonium nitrate and water. You pop the water and the ammonium nitrate dissolves, which requires a whole bunch of energy, which is yanked from the room temperature water, thus cooling it down, and ta-da! Instant cold pack. If you're saying, but wait, if this is a salt, what's the metal? Look, ammonium, the ion, ammonia kind of acts like a metal. It's weird. Just blame the hydrogens. So let's get to the melting thing. Water, under human tolerable conditions, exists in 3 phases. Solid, that's ice. Liquid, water, and gas. Steam and humidity are 2 familiar forms of this. Changing phase is an energy expensive proposition. The way the water molecules relate to each other alters quite a bit, and that takes energy. And at the temperature all these operations happen with water, the energy emitted or sucked up is in the range where we experience it as heat, temperature changes, unlike other stuff where we see color changes. But you can feel the heat energy being stolen from your body to melt ice if you hold it in your hand or suck on an ice cube. Brr. And people unfortunately feel a dump of energy when they get hit with steam as it changes from gas to liquid water. The big energy release when this happens is most of what causes a steam burn. So use hot pads in the kitchen is what I'm saying. When water is a gas, it's just out there, loose, far away from other stuff, so doesn't have a structure and doesn't really interact with other water or really much other stuff. But when it goes from gas to a liquid, weak polar bonds, positive to negative, are formed. This is what gives water the ability to form droplets and that surface tension skin thing you can rest a paperclip on. I mean, paperclips sink in water, they're metal, but the surface tension can hold a paperclip up if placed on there carefully. If you're bored, there are all sorts of fun surface tension tricks you can fiddle around with. Those bonds are loose and ever shifting. When water goes from a liquid to a solid, the bonds become more exact, more rigid, and stay in place, and energy is released. But when water goes from a solid with those rigid bonds to the more loosey-goosey liquid bonds, energy has to be absorbed. Okay, so how does this melting ice, this going from solid to a liquid and absorbing energy, make a liquid that's colder than solid ice? Energy is required to dissolve salts in liquids. Well, most salts, there's always an exception. And it takes energy for those rigid crystal bonds in ice to break apart and become the loosey-goosey liquid-water associations. Now, ice can snag that energy from the air if the air is warm enough. I mean, when it's really cold outside, ice doesn't melt. There's not enough energy for the ice to grab. It's at equilibrium. But gathering energy from the air isn't terribly efficient. If there's liquid around, well, that's much denser with matter and as a result is much more dense with energy. And so the melting process can pick up. This, by the way, is why snow crystals can fall out of the air as a solid, but then they hit the warmer ground, a solid, much more dense with energy, and melt. You can observe this yourself when it's snowing outside. But even if it's not snowing outside, if you have a glass of water at room temperature and put a piece of ice in it, and then have a piece of ice just sitting out in that same temperature air, the one in the liquid will melt faster. And the last piece of knowledge, solutions. Water with stuff dissolved in it freezes at lower temperatures than plain water. That's why vodka doesn't freeze in the freezer. The ethanol disrupts the formation of ice crystals. That's why people put out salt crystals of different sorts to prevent ice on streets and sidewalk. Because as the snow falls or little ice crystals form, teeny tiny pools of salt water stop the ice crystals from expanding. In fact, they melt and spread around more teeny tiny salty water, stopping the ice sheet from forming. And that's why it has to be colder for the ocean to freeze over than it does for freshwater ponds and lakes. The salt disrupts the ice crystals. And it's also why icebergs in the salty ocean are fresh water. When the ice finally does form, it pushes the salt from in between the water molecules out, and they snap together into pure ice crystals. So here we are. We have plain old water ice. Put it in a bowl. It starts to melt a little. The warmer than freezing air can have energy taken from it to pop the ice crystal bonds apart and change phase from solid to liquid. But this bowl of slowly melting plain water ice will never drop below the temperature water freezes at, 32 Fahrenheit or 0 C. But add in salt. Now you have a salt solution. Now you have a liquid that can get colder than the freezing temperature of water and still remain liquid. It has extra heat to give to the melting operation. So as those bonds are popped apart, more and more heat is stolen from the salt water solution. It stays liquid, but its temperature drops below freezing for the plain old water ice. You can get temperatures in a saltwater solution easily all the way down to 15 Fahrenheit or negative 10 C. And with some more salt, you can get things even colder. The coldest temperature chemically possible for this mixture is about negative 4 Fahrenheit or negative 20 C. But that's a lot of salt, like 20% salt to 80% water. But this is how bowls of ice with salt in it can be stirred to freeze ice blocks and make ice cream mixtures sitting in them. Freeze. Melting ice requires a lot of energy. Remember, phase changes are energy expensive propositions, and that will be stolen from any source that has more energy than the ice, the air, your hand, that salt water, because it's a liquid. So by definition, it's higher energy than the solid because it is a liquid, even if the temperature is lower. And so by being harder to freeze is how melting ice can steal heat from a saltwater solution and make it colder than the ice it's melting. It's wild at the phase change boundary. Strange things happen there. So thanks for coming along on this weird journey of energy, chemical bonds, and phase changes. Show notes for this episode will be at thehistoryofamericanfood.blogspot.com. Any email questions or quibbles will reach me at thehistoryofamericanfood@gmail.com. Even if you don't feel like writing a whole review, star ratings on your favorite podcast widget make this show more findable. So please take a few seconds to express your thoughts in gold stars, and if you have time, leave a review. Along with promised pictures and links, I'll include any interesting media I consumed for the episode. Music for this podcast is Fingerlympics by Dr. Turtle, and the link to the show notes is also in the show's Twitter and Insta bio at THOA Food and in the show description.